So this is we're going to start talking about a second way to multiply vectors. We've already talked about the dot or scalar product, and this other way is what's called the cross or vector product. This is a way of multiplying vectors where your end result is another vector. So let's say we had A cross B and we got vector C. There's one way that we can calculate the magnitude of vector C, and that's by doing the magnitude of vector A times the magnitude of vector B times the sine of the angle between them. Now, one thing to point out is that we can use a rule called the right-hand rule to determine which direction A cross B actually goes. The right-hand rule is the basis for, say, torque. If you've ever heard the saying righty-tighty, lefty-loosey when you talk about turning screws or bolts or nuts, that's really a factor of the right-hand rule. So in the right-hand rule, you take vector A and you point your hand in the direction of vector A, so your fingers point in the direction of vector A. The palm of your hand, or if you turn your fingers 90 degrees, they should point in the direction of vector B, or should point in the direction of vector B. And your thumb would tell you the direction of A cross B. Now it is worth pointing out, if you did B cross A, you get the opposite result. You get a vector of the same magnitude, just exactly opposite in direction. So this is an example of a computation which is not commutative, where the dot product A dot B and B dot A give you the same thing. Here A cross B and B cross A do not result in the same vector. They result in vectors of the same magnitude, just opposite directions. There is a second way to do the vector product, and the second way is a little bit more complicated and a little bit more advanced. And to kind of explain the second way, what I do is I start with a 3x3 matrix. I'm not 100% sure how many of you are familiar with matrices. You may potentially have seen them before. I remember maybe in pre-calculus or algebra 2 doing a little bit with matrices and how matrices work, but not very much. So in the 3x3 matrix, what I start is with my unit vectors I hat, j hat, k hat in the top row. In the next row, the x, y, and z components of A. And in the third row, the x, y, and z components of B. So the cross product of A cross B is what we call the determinant of this matrix. And so to show you how we calculate the determinant, what we do is we take those numbers, multiply them together, all of those multiplied together, and all of those multiplied together, and add those three numbers up. So that's the first step of calculating the determinant. The second step is to take all of these numbers, all of these numbers, all of these numbers, multiply each arrow together, and then subtract all those from the value. So what you end up with is something that looks like AYBZ I hat plus AZBX J hat plus AXBY K hat minus AZBY I hat minus AXBZ J hat minus AYBX K hat. So you end up with this expression here when you actually work it out. If you want to combine like terms, that's really what you end up with. So this would be something that is not on your equation sheet. It is one trick to deal with vectors. You might be asked some WebAssign questions on this. I have not seen many, if at all, any AP exam questions where you're required to do this technique to find the vector product. It is one technique that is a valid way to do it. You see it sometimes in the solution guide as a valid solution path, even though this is not necessarily the way they want you to do it. So where that technique really becomes helpful is if you have two vectors in unit vector notation. So let's take vector A is 5 I hat minus 3 j hat, and vector B is 9 I hat plus 4 j hat, and I want to find the angle between vector A and vector B. So one thing I could try to do is draw these two lines out and then try to find how those right triangles work. There's probably some trigonometry that I could do to do this, but I could also make use of the cross product to do this. So the cross product, A cross B cross C, is equal to, well, that long mess of stuff, which we can actually calculate out. -3 times 0 plus minus 0 times negative 3 because, well, the z components of both a and b are 0, plus 0 times 9 minus 5 times 0 j hat, plus 5 times 4 minus negative 3 times 9 k hat. So if you actually work this out, the vector c is 47 k hat. The other way you could have worked out the cross product is to take the magnitude of a times the magnitude of b times the sine of angle between them, and this is how we're going to find the angle. I know what the magnitude of c is, it's 47, so all I need to do is find the magnitudes of a and b, which are pretty easy to do, Pythagorean's theorem. And if I take the magnitude of c and divide by the magnitude of a times the magnitude of b, I get the sine of the angle between them. So there we go, I used Pythagorean's theorem to find those two magnitudes, plugged it all in, and then did inverse sine to find the angle. And so the angle between these is 54.9 degrees. This is one technique you could use to find the angle between two vectors, is to use cross product as a way to find that angle. You could also use dot product for that matter as well. And, well, we actually found, it asked me to find the vector product, so I would have had to do it this way. So the next thing to kind of point out is one of the best examples of the cross product in mechanics is torque. And that torque is equal to R cross F, where R is what we call the lever arm distance. It's basically the distance between your axis of rotation and the location where the force is acting on an object. And F is how big that force is. Now usually the way we talk about torque is in terms of angles, that the magnitude of torque is the magnitude of R times the magnitude of F times the sine of the angle between them. This particular method works very well if you want torques that are just counterclockwise or clockwise. If you're working with torques that could be in more than one direction, say I have both an X component and a Y component, then this maybe doesn't work as well. So let's look at a quick example problem. And here I've picked an object here pictured, pivots about point O, and I have three forces that act on the object. And I've got force A, which is 10 newtons, acts 8 meters away from O. Force B, 16 newtons, acts 4 meters from O. And force C is 19 newtons and is 3 meters from O. And I want to calculate the net torque on the object. So the net torque is going to be the torque caused by A plus the torque caused by C. And the reason why I know it's plus is that A looks like it's trying to rotate it counterclockwise. C would also be a counterclockwise torque. If you do the right-hand rule, you get something that points up, both of those. B is a counterclockwise, or both those are counterclockwise, excuse me. A and C are both counterclockwise, and B is clockwise. So what I could do is take magnitude times radius times sine of the angle between them. And once we get that, we get the net torque that acts on that object. So let's give a quick overview of the vector product and how we can use the vector product to talk about torque. In the next lesson, we're going to look at static equilibrium and look at some problems dealing with static equilibrium.